Well, last class, I'm so much used to computing molecular biology that it took for all the complete day that I forgot that our class finished early, so I didn't have enough time to do the exercise, but we will do exercise now. But before doing the exercise, I want to talk a little more about theory, because in fact there is a couple of points like why we use the tool, how we use the tools, and what else, how to understand the result. So the slides that we publish in a minute, but I want to keep some surprise. Just a little summary. We have spoken about global, semi-global, and local alignment. And essentially, there are three different questions, as you know, and you should keep in mind that there are three different questions for three different answers for three different questions. The word that I want to introduce here is subsequence. That I mean, I think it should be kind of obvious, but just in case, it essentially means the part of a bigger sequence. Okay. I mean, it's a technical name that I will use sometimes. So you have a complete sequence. If you want to do the global alignment, is the sequence to the sequence. And in the semi-global is a sequence to a subsequence. So the short, let's say the gene is a sequence, and the genome, you only match part of the genome. That's called the subsequence. Okay. Say yes, say no, move the head. Okay. Oh my gosh, my computer is opening too many windows. Okay, subsequent, don't get confused. So important thing in BLAST, you can read BLAST is local, and everything gets a score, and we have a threshold for the score, and normally that threshold is not chosen. I mean, in fact, I don't know a way to choose the score. We have a way to choose an e-value. And the full picture is this. We calculate the score when we compare two sequences, when we align two sequences. Essentially, when we compare two sequences or we align them, we assign the scores according to this substitution matrix. So the the score depends, of course, in the sequence, but also depends on the matrix. You change the matrix or you change the gapping cost, then the total score will change. The score is not a property of the sequence; it also depends on how you evaluate the way that you compare things. So it is important that you know how to compare the sequences. And in particular, the score doesn't depend on the database. The database that you are using is not in the formula for the score. The score depends on your query, on your subject, and on how you compare them, the score that has every pairing or the gaps, nothing else. So if you have two sequences, you can only calculate the score. On the other side, if you have a database, then you have an e-value. An e-value is a property of the database. Of course, it also depends on the sequence that you are using, but the basic question is depending on the database. If the database change, the e-value change. In particular, when the database get more sequences, the e-value change. So in general, we want to use a small database that contains all the sequences that are important for us. And the other point is that when you do the search, you should record what database did you use and when you use it. Because if someone wants to replicate, they should essentially test the same database. I'm sorry about the contrast here. I didn't check this one. So comparing two sequences gives you a distance, a number that is small. Aligning two sequences gives you a score, and searching a sequence in a database gives us an e-value. I will fix this slide. Okay. Okay, let me talk about the first topic of today. What is a computational cost? This is an important topic because, because essentially the point is this. There are several problems that we can solve in theory, but we cannot solve in practice. And it's essentially given because the solution that we have takes too much computer resources. It's too expensive in terms of computer. And it's super interesting that we have problems that have solution, but we will not be able to find them in our lifetime because we don't have the capacity of doing that. What is computational cost? Essentially, is how much time you take to solve a problem. For example, how much time you take to find the optimal alignment or search in the database. In some cases, instead of time, you count the memory. These are the two resources that we kept, time and memory. There is a trade-off in general, you know. If you have a lot of memory, you can save some time. And if you have a lot of time, you can use less memory. So these are kind of in opposite direction, kind of perpendicular. You can improve your memory, but there is a limit of your memory, and there is a limit of the time you can do. So, of course, you know, every time computers are faster and cheaper, and then you will say, it's not important. Next time I will have a faster computer, but there is a limit that you can do. I mean, there is a intrinsic hardness of the problem that is independent of the technology. Because even if the computer gets 10 times faster, or 100 times, or even let's say 1 million times faster, maybe the problem is still so hard that even with a computer 1 million times faster, it will not be solved. So in formal terms, computational the computational cost is how many steps we take. But the important steps here are how many comparisons we do, how many times we have to compare two things, or in some cases, depending on the problem, how many multiplications we have to do. In our case, for the alignment problem, the basic question is how many comparisons, how many times you take two letters and you compare them, how many times you take two amino acids and you go to the BLOSUM matrix and you search it. Okay, that is the limiting. That is the way that we will count. Of course, faster computer will do that faster, but the total time will be the speed of the computer multiplied by the number of comparisons that you need to do. So the basic question we have to answer is how many comparisons we need to do. And that essentially will be a formula that I here represent with the letter F, a function that depends on M and N, where M is the size of the query and N is the size of the subject. Okay? So then, so the computational cost will not be a number, will be a formula. What we will describe is the formula that explains how many. Shall I make a summary? People are arriving late. Well, if necessary, some of you can explain. So when you explain, you understand better. So we're looking for a formula that describes essentially how the number of comparisons depends on the input size. And that will tell us something about what problem can be solved in real life and what cannot be solved. So in general, except very crazy problems, the small sizes take shorter time and larger sizes take longer time. It's kind of obvious that if you have a small input, you can solve it faster. If the input is bigger, it will take longer, but how much longer? So normally you can develop a formula, you can essentially count things, and you will have an expression like this, like 100 times m squared times n to the 4th power. Now, in the big scheme of life, let's say if you have a computer that is 100 times faster, then this 100 will not count anymore. If you have a faster computer, you have a multiplication factor, like 10 times faster or 1 million times faster. So this constant number can change depending on the technology. So that is the part that we don't look. the important part for us is this. I wrote it on m squared. I'm sorry, I forgot to put the square here. I will fix this. So the important part is m squared times n fourth, and you will write here m squared times n to the fourth power, and we will say that the cost is on the order of. This is the keyword here. On the order of means that it's not exactly like that, but it is similar to m squared to n to the fourth power. Okay. Here I am just inventing the formula, just an example. But the basic idea is that you get kind of a big picture, and there is a notation for this. Is a big O. You can Google if you want to know more. Okay, I don't say that you must, but if you want to know more, you can search for this big O notation. That is an official thing, and it's super important. And it's kind of this is what really people do in computer science. This is computer science. How that is the question that people solve in computer science. The big O of different problems. So when we say that the cost, we will probably write with a formula with an O, essentially meaning that there is an m, there is an n to the fourth power, and there may be other numbers, but that other numbers are either constants or small numbers. This is the part that is dominating. The formula may be more complicated, but we simplify and we get essentially the biggest part. Okay? Any question? I mean, I don't want to go too much in detail because we are not doing computer science here, but just get an idea that what we are looking for is a formula, and the formula will give an idea of how hard things are. So, for example, in our case, for doing an alignment, we need to make the dot plot matrix, okay? We should have one row for every letter in the query and one column for every letter in the database, in the subject, okay? Therefore, you have a matrix that the memory that you need, it depends on m times n. And you have to fill that matrix and also times m times n. And then you have to find the diagonals, and well, that part is a little easier, or it's probably not harder than this one. So the computational cost of our problem is m times n. Okay, you got me? The computational cost is how the program, how the execution time of the program, or how the number of comparison depends on the size of the input. Okay, I see fixed faces like not understanding. Say yes, say no.
Maybe.
No. Thinking.
What is computational cost? I don't get it.
Computational cost is how much. The first approach is how much time takes to solve a problem, depending on the size of the input. You know that small size will take less time than big size. So if that is the case, what is the relationship between the size of the input and the time that it takes to solve? So let's go again. So the first approach is how much time take to solve a problem, or in some cases, the other part of the computational cost is how much memory you need. These are the two resources that you get: time and memory. To simplify things, we are going to talk about time, but eventually memory can be a problem. I mean, if to solve the problem you need memory that you cannot pay for, then you cannot solve the problem. If the time that takes to solve a problem is 3 centuries, then you will not solve it. So what is the thing that affects the time? It depends, for one side, on the technology, because you have faster computers. But when you get faster computer, you essentially make things to go 10 times faster or 1 million times faster, but it's a constant time. Okay? Then you still have a part of the cost that depends on the size of the input. So what I'm saying here is that we will get a formula. If you think about it, for example, this is an easy problem. Like to make the dot plot matrix, essentially we need memory to store the matrix, and we need time to fill the matrix. Okay. So it depends on the size of the matrix. What is the size of the matrix? Well, the number of rows, the number of columns. What is the number of rows? Well, it's the size of the query. What is the number of columns? The size of the subject. Okay. Therefore, the computational cost depends on M and N, like this one. Okay.
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 So then the memory that we need will depend on M and N, and they go multiplying. They are not adding, they are multiplying. And the time that you need to fill that matrix is also M times N. Okay. Fine. It's not so bad. I mean, there are systems that take more time. There are systems that take N squared or N cubed, and that is worse. I will show you a contrast, and you will see in a minute. I will give you numbers that will make it more clear.
Okay.
But so far, the point that you can see it is, if the query is 2 times bigger, then your time to make the matrix will be twice the time. If your subject is 2 times bigger, if the subject is 10 times bigger, then you will take 10 times more memory and 10 times more time. Is it true? Do you agree, let's say?
But you said they're on the opposite way.
Well, tell me.
Memory and time.
I mean, no, I'm not saying that they're opposite. Okay. No, what I say, yeah, I say something like that. But no, but to be precise is like this. In some problem, you can make a trade-off. You can, I mean, if you have memory, you can change your program to use more memory and less time. But once the program is fixed, we have a fixed idea. Just for example, the way that we explain the alignment, we need to build a matrix. And you need memory for that matrix, and you need time for that matrix. There is a solution. There is a way to do the problem that you use less memory, but you use twice more time. If you want to do alignment with larger matrices, they will not fit in the memory. And in that case, you need to change the program. But right now, don't get complicated. My point is that you have 2 things that you care: memory and time. And you care about both, because even if there is a trade-off, if you win in one side, you will lose in the other. So you need to care essentially about both things: how much memory you need and how much time you need. Okay.
Okay, I think with the example it will be better.
With example, no, don't depend on examples. Don't depend on examples. Try to understand. We need to count how much memory we need. We need to count how much time we need. The time is essentially the number of comparisons that we do. The number of times, the number of times that we take 2 letters and we compare them. Okay. Or in other words, the number of times that we look inside the Blossom matrix or the PAN matrix. Okay. And that number of times will be depending on the size of the query and the size of the subject. Okay. And the total memory will be the multiplication of M and N. And the total time will be also the multiplication of N and N. Therefore, if that is the time, if the time is the order of M times N, like I put here, then you will have the point that if the size of the query, this M, increases 10 times, then the alignment time will take 10 times longer. Okay, if the input increases 10 times, then the execution time increases 10 times. If the subject increases 10 times, then your execution time will be 10 times bigger. Yes, no? Essentially, because you realize that there is a matrix, and if you put 10 times more rows, then the area of the matrix, the size of the matrix, will be 10 times bigger. Or if you increase the number of columns, if you multiply by 10 the number of columns, then the total number of cells is 10 times bigger. And because you have a matrix. Okay?
Okay.
Okay, people are still sleeping. You need coffee. Okay. And I am trying to, I don't want to get to the hard part yet. So, I mean, I put this when you are in theory more awake. So there is a point that I don't want people to get confused. This is just a comment. There are two matrices that we work here, and I try to avoid confusing them. There is a substitution matrix that in our case are either 4 by 4 or 20 by 20, which is a kind of the Blossom matrix or the PAM matrices or the DNA substitution matrix. That is called the substitution matrix or scoring matrix. And these are square matrices and they are symmetrical. But we are not talking about this. That matrix is an input for you. I am giving you the Blossom matrix or the PAM matrix or the way that you will compare. That is an input. This is not the one that we are caring. We care about the dot plot matrix. Okay? And the other comment that I want to say before going is that for local alignment, we have two approaches. One is an ungapped local alignment, and essentially you are looking at subsequence that match exactly a subsequence in the subject. Remember, local alignment is subsequence in the query, aligned to subsequence in the subject. Okay, two small parts. In the simple version of BLAST, in the simple version of local alignment, you do it without gaps. Okay, in that case, you only do diagonals. And if you want to put gaps, then you need to move vertically and horizontally. And essentially, that makes the problem harder. Global and semi-global alignment always have gaps, at least external gaps. In local alignment, you have the option of doing it ungapped or with gap. Okay. Why you want to do this? Because somehow the ungapped is faster to do, easier to do, and it is important more, let's say, from the, I mean, it's easy to understand what it's doing. The gapped is probably better for biology, but it's harder problem. Okay, the ungapped is an easy problem, the gapped is a hard problem. Even if you want to do, I mean, you probably want to do gaps anyway. What I mean is this. Sometimes we need to simplify the problem and do something that is not 100% correct, but it's easy to understand. Okay, that is the role of the ungapped. And historically, it worked because the first version of these tools were using ungapped alignment. Okay, any question before we go to a practical thing and an exercise? So these last two slides are just comment, okay? I'm just commenting that we are working in the dot plot matrix, not in the Blossom matrix. And we have different ways to look in diagonals, and the diagonals are the important part. Okay. I have a text here, and I will challenge you to this question. Okay, probably we're not going to do. I can send you the text if you really want to have it, but the trick is that you do it by hand, not with Control F. So, for example, I am giving you some word. Let's look for the word "and." How you find the word "and" in a text like this? How you do this? How you find it?
Search like one by one until
Yeah,
I
exactly.
saw the end.
Exactly. You go by one. You take the first one. I mean, there are different ways to think, but let's say that you go word by word, and you take the first word and you compare the first word with this, and then you compare the second, and they compare. So basically, how many comparisons you need to do? How much time will take it to search inside here? In other words, you can even see what is the next slide. What is the cost?
Word number?
The word number, exactly. The word number, that is to give you the number of pages that you have to compare, but then you have to compare every time that you compare two words, you need to consider the length of the query. I mean, looking for "and" is harder than looking for "it." And looking for "it" is as difficult as looking for in the sense that this has two letters, this has two letters, and this has three letters. So when I have three letters, I have to compare three letters to whatever I have in the subject. Okay. So for example, if the subject is "not," I have to compare every one of the letters. Okay, if you are clever, you stop at the first time that you find something that is different. But to make it more realistic, like if you are counting mismatch, you will need to compare each one of the letters. So it will depend on the size of the query, on the size of the subject. If you have three letters, or I don't know, 7 letters, and will depend on the number of words. Okay, three components. Size of query, size of subject, and number of words. Do you agree? Say no if you don't agree. Say yes if you agree. Say something. Say I don't understand if you don't understand, but say something.
Is it number of words or number of letters? I'm confused.
Number of letters. And well, there are two questions. The size of the subject is number of letters. The size of the query is number of letters. Because the number of comparison, remember, is letter to letter. But you also need to take in account the number of words, because the number of words is the size of your database, essentially. Think of this. This is an example. This is a gene that you are looking for, or a protein. Let's say that you are looking for a protein, and your database is a list of different proteins. So when you search a text in a database, you have two components. One is the length of the comparison, let's say, of when you compare two sequences. And that we know is m times n, okay? The size of the query, the size of the subject. When you fix the subject, you need m times n, okay? But in a database, you have another component that is the size of the database. How many words are in the database? Comparing two letters, two words, this and this, for example, will take m times n. Okay, m is the size of the query, n is the size of the subject. But then you have to repeat for the next one, and for the next one, and for the next one, and for the next one. Sorry, this one. Okay, you need to do this over and over again. So you have one part that depends on the number of words, and one part that depends on the size of the words. Okay. And will also, of course, depends on the size of the query. If you have a longer query, you will need to compare the query with longer times. No? So you can see essentially what's happening with BLAST. Remember that in the local alignment, like BLAST, you need to make a matrix with the query and the subject. And the database has many subjects, so you have to make a matrix for the first, then a matrix for the second, then a matrix for the... For every word in the database, you need to make a matrix. Okay? Building that matrix takes m times n. Okay? But then depends on the size of the database. The bigger the database, the more you have to make more and more matrices. Do you agree? Okay, one please. Ramal is kind of regretting everything now. Yeah. We have two Atakan and they are hiding themselves. So do you agree that the bigger the database, it will be harder? And the bigger the query, it will be harder. And the bigger the size of the subject, it will be harder. Okay, to simplify ideas, we are going to imagine, because the argument will be correct anyway, that all the subjects have the same size. In practice, you see some are shorter, some are longer, but they will have an average, and we will think like they are all the same size. So what was the cost? Okay, if the query has size m, like before, and the average subject length is n, you can imagine that all have the same length, just to fix your idea. Every time you compare two words, you need m times n, like before, because you need to make the matrix, okay? And searching the database takes m times n times d. D is the size of the database. Okay, D is the number of subjects in the database. Agree? Say something. The tool is like frozen.
Yeah.
Subjects in the database means are resolved?
No, no. Subjects are the input. No, it's not the result. It's the thing that are in the database. Remember, every day you make a comparison, you have two components: the query that you are looking for and the subject that is one of the entries in the database. The database essentially is a list of a set, if you like, of subjects. These are not results yet. These are just searching. We don't know if they are going to be successful or not. We are just saying that every entry in the database is a subject, and this depends on the number of entries on the database, the number of subjects. Okay.
Okay.
Yeah. A subject is not necessarily a result. It will be a result if the score is over a threshold. So this gives you m times n times d. In other words, well, you realize that, okay, let's be more clear. If I want to find all the times that there is an here, I have to read all the text. Okay, I have no option but to search everything. Okay, until the last one. Because until I have seen the last one, I don't know if I have seen all of them. Maybe the first is easy to find. Okay, maybe this one, but I want to find all of them, not only the first one. So I have to look until the end of the database. Okay.
Why it says without gaps full word if it's a local alignment?
No, I just for the practice for this exercise, I am asking you to find.
It's just our query, right?
Yeah. For this example, yes. No, in general, you want with gaps and local alignment. But for this practice, with an exact search, what I mean is that this is a match. But for example, this income, I don't want income to match with in, at least not so far. Okay. I'm essentially telling you, this is the most simple problem that you have. Perfect match, exact match is the easy one. If you want to do with gaps, then it becomes more and more complicated. So I am giving you the easy exercise. And what I'm saying that even the easy one is still complicated because you have to go word by word, take the first, this is in, this is not. You have to go one by one and compare the first, compare the second, compare the third. Okay? Fine?
Yes.
Good question. So now try this. Here, for your happiness, I make an index. You know what is an index, no? It's like when you have a book, like Bioinformatics for Dummies. You, in the last page, you have this thing, this one. that is typically in the last pages. That says for you have an alphabetical order of keywords, and in the side they say in which page you can find. If you want to say, for example, let's say blast. And say blast is say look for basic. Look, let's say basic. Okay, basic. See, funny. C blast. And you go blast C. Okay, but anyway, they're kind of circular. But here you have alphabetical search. How you use an alphabetical index? Do you know indices? No. How you use this index? Or let me ask another way. Do we want? There is any advantage of having this sorted alphabetically?
Yes, of course, there's an advantage.
What is the advantage?
That I don't have to look one by one every word. It says me where is it.
Okay. How we use it? How we search? Let's say, for example, let's search for and.
We don't need to look at all the words. We just need to focus on the words start with N, A, sorry. So we might group them as, together.
Okay, you essentially look for the first letter. Okay, that is an approach. So, okay, so how we find it? So you have to count A. You have to compare the first word. You have to compare word by word. And if you know, if you go to B, you are too far away. But that is kind of so dividing the problem by the first word, essentially. If the first word is A, the first letter is A, you look only in the first letter. I think it can be better. I think it can be better. Do you have any better idea to use a sorted list? For example, to look for in. How you look for in? Because and is kind of at the beginning, but in is somewhere in the middle. How you look for in?
Version.
Sorry, Ramal, I cannot hear you. Ramal is talking, but the microphone is not working.
Trial version.
So if it's alphabetical order, then we might as well say I is, let's say, 15th letter of the alphabet. Then we look for maybe that part.
Okay, it's an idea that you think that essentially you assume that Ramal, you need to fix your microphone. I see you, but no, I cannot hear you. There is a test, but sorry, we cannot hear you. The Ahmed idea is that if we have the 15 letter, we go to the 15%, like we divide the list in more or less equal parts, but then you are assuming that every letter is using the same frequency, and that is not true. In English in particular, we know that vowels are more common than non-vowels. I mean, how many words with W you have in Turkish? Or with Q? How many letters with will you have in English? Now that depends on the language, and depends on. But there is an idea like that. I will tell you what we do. What we do is we go to the middle, and we compare the letter, the middle word with the word that we are looking. For example, with in. So in the I is comes before than L. Therefore, I know that it cannot be after lentil. All this part is useless for me, so I ignore it. I divided the problem by half. And then I go to half of what is remaining, more or less here, and I compare. This is too little. Then I go to the middle of this, and I got somewhere like here. Ah, found it. So essentially what we do, we start from the middle, because it's sorted, so you can start from the middle and you compare. And the comparison essentially gives you three options. You found it, it is before or it's after. And with that decision, you discard half of the database, of the index. Okay. And after you discard that, you go to the half of the remaining part. So you divide the list in half in every step. And that guarantee that in quick time, you will find it.
So we can decrease the cost in that way, right?
Exactly, exactly. That is exactly the point. That is exactly the point we discussed. Okay, there is a trade-off, as you see. So, well, this example
Teacher,
works.
with this vocabulary thing,
The
dictionary.
index.
So with the letters, we learn it by their row. When we go into middle, going backwards, it's kind of harder than going in the.
Why?
Because we learn it by the row. We learn it like A, B, C, D,
Okay.
and
Okay.
it's like it's coded like this in our brain. So when we go to the L, for example, going backwards is harder. Because, for example, try to count the alphabet backwards.
Just practice. Just practice. Because you learn in a way, as you say, but you learn the other way and you still do backward. But in fact, you don't need to know. You only need to know which comes first. You know that I come before L and that I come after F in the alphabet. You don't need to count backward. You need to know before or after, and then you move in the row. Now, notice that there are two steps here. One is finding the letter, and then you get all the positions. This is, by the way, row and column. For example, you say at the beginning of the first line, at the beginning of the third line, the second in the seventh line. Let's say 1, 1, 3, 1, 7, 2. So this is the first and the first in the third, 4, 5, 6, 7, the second, this one. So this is in. So yeah, the index help us to find quickly. There are two parts. One is finding the keyword in the index and then following the index. Okay, the index has pointed. So with the index is much faster. As Arda says, it's much faster to find once you find it. Okay. No.
What if
Yeah.
the word was ini, maybe?
Sorry.
What if the word was ini, maybe? Like there were two I in the word and it repeats.
Like E-E-N? No.
I
Can you write
and
in the chat?
I and
Yeah,
I.
Ini. Okay.
Yes.
Ini. Okay.
So I would be repeated.
No, why? I don't follow you.
I mean, you search for I coming before the in the first letter in the word. So you eliminate the others after the L.
Yes.
What if the I coming in the last part again?
Nothing happened. I already discovered. I don't get your question really. Can you ask in a different way?
Maybe I got it wrong.
Remember that we are looking complete words.
Yes.
Okay. Therefore, if the first letter doesn't match, I don't care if the following letter match. If the first letter is wrong, then I don't care about the rest. The first letter has to be right. If the first letter is not correct, I don't care.
Okay.
I discarded. I know that the L, because it's a perfect match, not partial match. I'm not doing a local alignment, I'm doing complete match. So the only way that I will find in is in. It's a perfect match.
Okay.
For example, is not income, is not infatuation, is not interminable, it's just in. Okay? It's not this in inside interminable. No, it's not. It's the word in versus the word in. Perfect match. So the basic idea that I want you to get is that when the index is sorted, when you have a sorted list, it is easier to find because you have a strategy that is essentially dividing the problem in half every step to making it easier and lower cost. Okay?
Okay.
Yes, no? Yes. Okay, so so that is the idea of the index. It works. It works for exact match. It has to be exact to work the way that we're doing. This index is not used instead of the original text. We still need to have the original text. Okay, so it's like the same as the index in the book. You still need to have the book. The index is an extra. Okay, the index takes a few pages. It's not the book. It's a complement to the book. Therefore, what I mean is that the index takes extra space. And that is what I was trying to explain before. In this case, we can do it faster. We can do faster, but taking more memory. We make the trade-off of using more storage and on the other side, saving time. Okay, and that is going to be always the case. Most bioinformatics tools will do something like this. Okay. Questions? So, what is the cost for searching a sorted file? Okay, I will give you this. We don't necessarily need to go directly, but you can check it later if you like. If the database is a series of subjects, subject 1 to subject D. Okay, D is the number of subjects in the database size. And I am using mathematical notation, by the way, because 100% of the people who voted say that they like a mathematical notation. Okay, 100%. One people, but they were 100%. So we need a lower bound. L means lower and U being upper. And essentially, you take the middle, U minus L divided by 2, the midpoint. No, maybe it's a plus. I'm not sure now. Oh, no, yeah, it should be plus. Okay, it's the midpoint. Then you compare your query to the subject in that position. If it's equal, you found it. If it's less than, you drop 1/2 and you change the upper limit. If you are over the subject, then you know it's the second half, and you essentially can ignore half of the database every time. So this you can check it later. It's not critical right now because it's just the idea that I explained with the graphical thing that you go half in every time. The important point here is that we discard half of the database every comparison. So essentially, since we divide by 2, essentially you can, well, this probably you need a second to think. The point is that instead of comparing with all the database, I compare with the logarithm in base 2 of the database. Let's say this, if you have 1,000, if the database was 1,000 words, first you compare, in the one comparison, you get, you discard half and you get 500. In the second, you get 250. In the third, you get 125. In the fourth, you got what? 65, 67. Okay? Then you divide again, and you get 67 or 167. No, 62. Then you divide, you get 31. You divide again, you get 60. Then 8, then 4, then 2, and eventually you will find it. The worst case you do in 10 steps. And 10 is the logarithm of 1000 in base 2. Okay? I tell you, the only mathematics that you need to know is logarithm. For molecular biology, the logarithm and exponential are the only thing that you really need to understand well. Okay? So notice the difference. If we don't have an index, the cost is m times n times d. If we have the index, is m times n times logarithm of d. Okay? And now we need numbers. I will show you the numbers, and then we see if you have questions. To fix idea. Think that you have a query with 100 letters, like a gene that you're looking at, protein with 100. Just to fix ideas. It can be more, can be less, but you know what will happen. And also n the same size, so that is not the problem. The problem is what is the size of the database. And we also, just to simplify the idea, assume that the computer can compare 1 million letters in every second. Okay? So what happened? If you don't have an index, how many comparisons? This is the size of the database. 1,000, 10,000, 100,000, 1 million, and 1,000 million. Okay? And you can go further, but just to fix the idea. Without index, doing essentially the matrix, doing only the matrix, the way that we say, you take 10 seconds, then you get almost 2 minutes, more than 15 minutes, almost 3 hours, 2 days, no, 1.5 days, 1.2 days, 11 days, 115 days. Okay? And I am assuming a database that is not very big for a genomic database. I am assuming a query that is not very big and a subject that is not very big. Most of the time, this is going to be more 1,000 or 2,000 or something. Well, it depends. But let's say that you are looking for a 16S, this will be 1,000, and this will be 1,000, and this database may be much bigger. So if you don't have an index, it will take many, many days. But Ahmed needs coffee. Okay, we will have a break soon. Okay, and yeah, everybody needs coffee. Yes, I need coffee. With index, which is essentially taking the logarithm of the previous number, the time go from 0.1 second to 0.3 seconds. Okay, this is the power of the index. This is why people use indices. Okay, this is what all bioinformatics, and I will tell you more. One of the key points in databases is indices. Indices is kind of the superpower of the computer. It came when you use indices, when you have a way to look efficient. Just look the difference. In one case, you have, I don't know, 4 months. In the other case, you have 0.3 seconds. Okay? And this is not a crazy idea. You can replicate the computation that I did here. But this is not a crazy idea. This is what we call cost. So there are many other ways. I show you one of the simple ideas that's called binary search. You have something sorted alphabetically or sorted anyway, and you divide in half. So that is called binary search, and it's kind of one of the good methods. There are many others. They are kind of more smart. I mean, like I made the idea that instead of dividing in 2, we can divide it in 10 or divide it in 25 or something. That people can do that thing, and divide it by the first letter or something like that. There are many, many ways. And that is computer science. That is kind of all the thing, not all, but one big part of the thing that people do in computer science is finding good ways to do these indices. But there is, of course, a trade-off, because to have a good index, you need more memory to store that index. So, so yeah, different people, every time there is a new program, not every time, but most of the time when you have a new program, it is because they are using a new kind of index. The way of doing index change every time, and they will make it either faster for some problem or easier for some problem. Okay. Now, what is the problem with this approach? It is a point a little in the direction of Aslenur's question.
Maybe.
What do you think is the problem here?
Well, I think we only have 4 letters like ACGT. That might be something.
Yeah, eventually, but not so far. If you have the 4 letters, in fact, people can do it with binary, with 1s and 0. No, at this level, it's not a big problem, the size of the alphabet, because you still have the protein case, and the protein case is still a decent number of letters. No, it's not a limiting. The basic point is that we assumed, all the discussion was assuming exact match. Remember, as Linda's question was, what if we have the inside the other word? In other words, what I understood of the question was, what if we are looking for a partial match, or a local alignment? Or what if we want to put gaps? Or what if we want to do something? So how we extend this idea of perfect match to partial match? And the clever idea is this: if you make an assumption, let's say that there will be no more than 3 mismatches, I am saying mismatch gaps or indels, then you can essentially separate the query in 4 parts. If you have up to 3 mismatches, one of the 4 parts has to be perfect. Because if, let's say that you have this 4 part, 1, 2, 3, 4. You can have mismatch here, here, and here, but this has to be perfect. I mean, since you have more parts than mismatch, at least one of the parts must not have mismatch. You can even be lucky, like all the mismatches are in the first and the other 3 are perfect. So the idea is to divide the word or the query in smaller parts and guarantee that the small parts are going to be perfect. Okay? You can only do that if you know how many mismatches. So essentially, you have the trade-off to say, okay, I will make a database assuming that there will be a limited amount of mismatches, which in biology essentially translates assuming that some kind of evolutionary distance. Okay? Any question? Did you get the idea that if we divide the query in small parts, one of the parts will be perfect match, and we still can use an index? Okay?
Yes.
Yeah, good. I'm still thinking that the tool is a recording because she's not moving. I think she's a recording. Okay, so in general, if you want to look with n mismatch, you can split in n plus 1 part, and one of the parts will have a perfect match. And why is important? Because this is how BLAST works. This is the trick of BLAST. BLAST uses an index to find the initial hit. So BLAST is not making the matrix. It's first using an index to find one perfect match and then makes the matrix around that match. Okay, that is the basic idea. So there is a key parameter, and that is, well, one of the reasons why I'm showing you this, there are three reasons about this class, but one of the reasons is this. BLAST has a parameter that is only because they use indices, that you have to choose what is the word size. In other words, what is the size that you expect to have perfect match? Okay? Like if you have 1,000 letters and you say, okay, at least 100 letters should be perfect, or at least 10 letters should be perfect. What is the minimum size of a word that should have perfect match? So BLAST can start then doing the matrix around that match. Okay. Ahmed has real question mark in the face. Let's say this. I will. Okay, let me show you the next slide. You have a parameter that I will show you in a minute. The parameter is called word size. And when you say word size, you will have the option of making it very big, in which case the size will be very fast, essentially because big words don't happen very often. So it will quickly find all the places where that big word exists. But you have the risk if the word is very big that if they appear with a mismatch, then you will not see them. What I mean is that, okay, let me say again. Let's say that the query is 100 letters, okay? And you expect to have 3 mismatch. So you divide 25, 25, 25, 25. Your word size will be 25, okay? Your query is 100 letters, and you divide in block of 25, 25, 25, 25, and you look the 25 subwords separately. Since you think that there will be 3 mismatch, one of them is going to be successful, at least one, maybe more. Okay. Now, if you are unlucky, and instead of 3 mismatch, there are 5 mismatch, you are in trouble. You cannot be sure that one of the 25 letters will match. In that case, you need to divide not by what they say, not by 4, you need to divide by 7 or 8. So let's say in that case, you can use a word size of 12, for example. You will have shorter word size, and you have to look each one of the subwords of size 12. One of them is going to match, and then you will have a bigger case. But that will take longer. The bigger the word size, the faster the search, but you may miss some subjects that have too many gaps, too many mismatch. Small words are more sensitive. You will find more things, but they will take longer. You know, Yahya got the sun in the face. I don't know if he's thinking or like.
I don't understand why small word size takes longer time.
But it's a good question. It's a good question. It's not obvious from what I'm saying. It's not obvious. The main reason is it's a little more subtle, but let me go back to the index idea. It's a more delicate thing, but the basic idea is this: large words probably appear only once. I mean, long sequences are not very common. So if you find them, you find all the versions ready. It's yes or no. Short words tend to appear several times. So you have to see, is this one is this one, is this one. Okay, so the index, as you see, has two parts: the keyword and then a list of possible places. Short word will have a longer list. Long words appear only one. Management only one time. Made 4 times. You can even see that the shorter the words, they tend to happen more often. And in genomics, so look, off appears a lot of times. So checking all times you see off will take a lot of time. So in general, in genomics, that is kind of easy to see. The shorter the word that you are looking for, the more times you will find. But remember, let me say in a way. This is, by the way, we are finishing the discussion and we will go for the coffee break. The basic idea is, are we here? No. Here I say that here. BLAST use the index to look for an initial hit. So BLAST is not telling you that now we found it. The index is only telling you BLAST what is the starting point, and then it tries to extend it. Okay, and that extension will say, okay, did we find all the sequence? Can we do the matrix with a long enough sequence or not? And that we don't know. The index is not enough. The index is only half of the problem. The index will tell you where to look for. But in many cases, that search will be unsuccessful. So the shorter words will give you more hits that will not be successful. Okay?
Okay, I got it. Thank you.
Yeah, but it's a good question. That is a question that I didn't write a slide, and I was waiting to see if someone asked it. So you have to understand something. There are always many subtle parts that I am not putting everything, because if I tell everything, it tends to be more confusing. I wait you to raise some question. There are kind of answers that can only be given if you ask the question. If I give you the answer and you didn't ask the question, it tends to be more confusing. So try to ask the question. If something you don't understand, ask it, because in many cases I am putting the question apart. Okay? So BLAST is not guaranteeing that we find everything. Okay? In particular, if you use words that are very large, it is very fast, but they may miss subject with some mismatch. So BLAST may lose some. In particular, if you're looking for sequences that are very different. Okay, if you have many mismatch, many indels, or many gaps, BLAST may not find them.
I have a question.
Ask.
But what if our subject is large? Then the thing is, it will be like the opposite of each other. Then the larger will be like more sensitive, and the shorter will a lot of mismatch. Am I getting it wrong?
No, I think it's a good question.
I know that we are not looking for all the sequences with this subject. We are looking subsequences. But what if we are looking for large subjects?
Yeah, okay. The point is this: the index depends on this parameter. When we
By
fix
the way, there is another question on the chat.
I know. I see. But let's finish this one. Yeah, let's see. The keyword here is the word size. When you choose the word size, all the index will be fixed on that word size, and you don't care anymore for the index. You don't care anymore about the size of the query or the size of the subject. You only care about the word size. Okay, because the index will have only words of a fixed size. Okay, if the subject is it's like here, for example, when I build the index, I didn't care about the length of the line. Okay, only about the word size. Now, the second part is in the extension. When the subjects are longer, then the extensions are longer. So the size of the query and the size of the subject depends, affect the extension, but not the initial hit. The initial hit depends only on the word size. Okay? Yes? No? So the problem is separated in two parts. Finding an initial hit that you do with an index and the index has a fixed size, and finding the extension. And that extension uses all the sequence. Yes, no?
Okay. Okay.
Okay, can we also say that short words that include index some way are more similar to each other? No, they are not more similar than I mean, we can say whatever, but the question is what we want to define that's more similar. Just remember that in the index, we don't look for similar, we look for exact match. Indexes are exactly exact match. Now, in and inter are more similar in the sense that you need more, you need 3 gaps between in and inter. And in international, you need more gaps. But that is again an extension question. It's not an index question. Index only find perfect match. Okay, that later you can extend, but the index only find the perfect match. I see many question marks in the face. Don't cry. Okay, what you need to get in at the end is this. Looking for a complete alignment, doing the alignment in a perfect way takes a lot of time. And even with the best computer that we have, it will take forever. So, and even with the best computer that can theoretically be built, it's a problem that has no solution in human life. It cannot be solved given the way that computers work. It's really something beyond our capability of understanding. So we need to do an approximation. And the approximation that we use in BLAST is based on indices. Indices are the basic tool that we use here. And here is the last word that I want to present you today, the idea of an heuristic. An heuristic is an approximation. So it gives you the correct answer to a similar question. Essentially, an heuristic is when you simplify the problem and you answer a question that is similar, but is not exactly the same. Since the original question is very hard, you simplify the question and you answer a simpler question, but you can answer. And the basic point is that you want that the simple question to be not very different from the original one. They may not be exactly, so essentially you will get an approximate answer. You want that the approximation to be good, to be not very different. That is what we call an heuristic. And it's a keyword that you can Google it. Okay. So to finish, I have 2 more slides and we go for the break. An algorithm is a protocol that will always give you a result. In particular, it came, for algorithm, you probably know from for algorithmy. And Al-Khwarizmi was the guy essentially who wrote the book and teach everybody how to divide numbers, how to do the computation. And every step when you take two big numbers and you have to divide 1, 2, 3, 4, 5 divided by 3, 4, 5, 6, 7, 8, the way that you do step by step, that is kind of algorithm. When you do multiplications and divisions and things like that. That is the first idea of an algorithm. And technically, an algorithm delivers a correct answer in a fixed number of steps. I mean, not fixed, but finite number. It will finish eventually. Now, that finite number of steps can be too big. I mean, like centuries. So an heuristic is a protocol that solves a simplified problem, not the original problem, or give an approximate answer. For example, when you do sampling, you grow, I don't know, plants, or you prepare some culture, you cannot test everything because you will destroy everything or it will be too expensive or whatever. So what you do, you take a sample and you evaluate part of it. That sample will give you an approximate answer, but it's cheaper and faster. I mean, if you want to know, for example, the average weight of the Turkish population, the correct answer will be to weight everybody in the country. And that is super expensive and super long. What the people do instead is they take a sample, and I don't know, 1,000 people, and they weight 1,000 people, and from that 1,000 people, you can go and try to generalize to everybody. Same when people play chess, in particular when computer play chess, the number of combinations in chess is so big that there is no way that the computer can approximate everything. There is a moment that they say, okay, I think like they have shortcuts. They can make mistakes. That is why chess is still an interesting game, because you cannot test all combinations. There are too many. I mean, in theory, you can solve it completely. You can check all combinations. The number of combinations is a big number, but you can eventually finish. The problem is that you finish after the university finishes. So the chess is so complex that it takes forever. I mean, not forever. That is the point. It doesn't take forever. It just takes several thousand million years. But it can be solved. So an algorithm will always work, but that time can be too much. And that is why the computational time is important, because it will tell you when the problem can really be solved in the time that you need. Essentially, you always need it for yesterday. So you need to use a tool that will give you a fast answer. So again, the heuristic is an approximate answer, a simplified problem. And if you know your history, you will see that this is a joke that even for Nasruddin Hoxha legend. I didn't find with Nasruddin, but I found this joke. And this is the same story that you got with Nasruddin and all time. Like, I'm looking for my quarter, for my key, something. I drop a key, I drop something. Did you drop it here? No, I dropped it 2 blocks down the street. Then why are you looking for here? Because here the light is better. So that is an heuristic. You don't look in the correct place, you look where it is easy to find. Okay? That is BLAST. You look the easy, not the correct one. So, and this is important because most bioinformatics tools, most of them are heuristics, because the bioinformatic problems are too complex to be solved exactly. In particular, multiple alignment that we will talk later, it is mostly about heuristic, because we will see quickly it is too hard to be solved correctly. Unless this the summary. Well, this is the summary. No? Computational cost is either the number of steps or the memory. We don't care about the detail. We care about the order of magnitude, and the big O notation essentially says this: the order of. Then we learn that indices are used to speed up search, and we can measure that speed up with the big O notation. And moreover, indices can be used that they're initially made for exact search. We can extend the idea to partial match by dividing the query in small parts. And then we learned that this is what BLAST did, and BLAST is therefore not an exact solution, it's an approximate solution, therefore an heuristic. An heuristic is a word that I want to introduce today. It means a protocol that finds an approximate answer. And that is what we had to talk before the coffee break. Fine? Any question?
We
Fine,
overlooked the
thank you.
question in the chat, by the way.
What the Aslinor question, but I answered it. I said the answer was this. The comparison between in and inter is about gaps. Okay? Therefore, these are approximate search, but I insist that the indices look for exact match, not for approximate match. But then when you got an exact match, you can extend that and see if they are similar. Now, in the example I give you English words because they are easy to understand, I believe. In DNA or genomic sequences, you don't have words, you have only sequences, the no space. Maybe next time I will show you directly letters. Maybe we can make an exercise with just protein letters, amino acid letters, to see if it's clear. I try to use human language because I believe it's easy to understand, but if you get confused, just think about words of fixed size. Okay?